Hi, I'm Anton Frablewski, and it's time for a little bit of geological myth busting, specifically some paleogeographic myth busting. You know, as a grad student in the 90s, I was always impressed with paleogeographic maps of the Western Interior, the Cretaceous Western Interior Seaway. They always had very high resolution of the shorelines with all the ammonite zones, you know, kind of coming and going, the regression, transgression episodes. I always thought that was really interesting because when you hit the latest Cretaceous into the Paleocene, it's gone. The seaway just vanished. Anytime I would ask a professor or, you know, somebody who's working on the Western Interior what happened to the seaway, the answer was always, well, it regressed, it vanished. And I always thought that was a little bit odd. You know, the Cannonball Seaway showed up in the Paleocene, but what happened in the meantime? So I'm sitting here in the early Paleocene part of the Fort Union equivalent Ferris Formation. Just about everything you'll read on the Fort Union or the Ferris Formation mentions the extensive coal seams and the sand bodies and the conglomerate, and true, it's got all of that. And since the early days of the 1900s when it was first described, the abundance of terrestrial plant material and conglomerates led everyone to suggest that, well, it's obviously continental, nothing marine about it. And that was the viewpoint until about the late 1990s. And as a grad student, you know, as grad students, we all like questioning authority and creating trouble and causing problems. So I started looking at some of these rocks and finding some really interesting little features, like these things, like that, and something didn't jive with it. They looked like marine trace fossils. So I did a little bit more research, and over the years I've continued to come out here and continue to work on it as I learn more. And lo and behold, this is a marine tongue of the Ferris Formation. So these traces here, things like this, that's Roselia. It's a polychaete burrow made by a terebellid polychaete that burrows down vertically and extends its little tentacles out to grab food. Lines its burrow with these kind of concentric rings of silt and mud, and it's got the stem coming down where the little body is. Here's another one. Here's some more. This rock is chock full of them. Now, I mentioned the Cannonball Formation. There's a section that Ed Belt had described up in Montana, southeastern Montana, and the Dakotas, and it's an estuarine brackish water arm of the Cannonball. So it sure looks like we have the same thing going on here in the Ferris Formation. Now, not just Roselia, but there's also little things like this. I spent a couple of minutes walking around just now and found this. It's not very exciting to look at, but it's a little plug-shaped burrow called Bergaria, and there's a bunch of these things around. They're all over the place out here. There's also our friend Rhizocorallium, and I did a video on these guys in the Jurassic, in the Sundance Formation, but they're also here in the Paleocene. You can see that nice classic U-shaped, and there's Sprida in there. Here's another one, nice specimen. So we've got Rhizocorallium, Bergaria, we've got Roselia, we have a variety of other trace fossils. So this is a brackish water to marine fauna in the Paleocene. So the paradigm of this being a big continental, non-marine, coal swamp, alluvial plain environment throughout the Paleocene is really not correct. And it took looking at trace fossils, as well as some of the tidal facies in the channels, to really demonstrate that. So, you know, trace fossils can be really important. A lot of times they're overlooked. Even today they're overlooked. A lot of people give them a lot of lip service, but they're not really utilized to the extent that they could be. So as always, or as usual, I've got a whiteboard kind of cartoon explaining this. And the traces I just showed you are things like Roselia, which is made by a terebellid polychaete, Bergaria, Rhizocorallium. And the little paleogeographic map off to the side shows the embayments of the seaway. The X marks the spot where we are now in Wyoming. That big arm to the north is up in the Wind River Basin, and that's the Waltman Shale, which has been interpreted variously as brackish water marine or lacustrine. I think based on data from here in southern Wyoming and the Hanna Basin, it's a safe bet that that lacustrine lake is probably at least partly brackish. So there's a couple of more transgressive episodes like this in the Paleocene strata of southern Wyoming. There's some new paleogeographic maps coming out, some new interpretations. But I just thought it'd be kind of interesting to kind of look at a well-established paradigm and flip it on its head by looking at some of the trace fossils in here. So, you know, key takeaways, look at trace fossils. They can be very important. These are marine traces. There's nothing like these in fresh water. We have two choices here. Either we have the very first freshwater record of these marine traces, or we've got a marine arm of the Seaway coming in. And I'll put my money on the second one as the most parsimonious of the two. So, again, as always, if you're a geologist or a geoscientist, step away from the computer, get outside, look at some rocks, question previous publications, question the established geographic maps, paleogeographic maps. Blakeygrams and scotisograms are fantastic, but they're not always right. Get out there, check for yourself. You'll be glad you did. Thanks for watching.